Welcome to qnawire.
We're given a copper wire with a square cross-sectional area and the length of a side of the cross-sectional area that corresponds to the cross-sectional area is 2.3 millimeters. And the length of the wire is 4 meters. And we're told that a current of 3.6 amperes flows through this wire, and it has a free electron density of 8.5 times 10 to the 28 per meter cube. I've given a little diagram over here um, just to show that we have deviated from the normal cylindrical wire, and here instead we have a square wire. And the things we were asked to find, we'll do on the next page. So we're asked to find here in part A the resistivity of we're asked to find the current density of this wire. So the current density is defined as the current over the cross-sectional area. And this is given in equation 25.3. But we already know the current, so this is given to us. The current is 3.6 amperes. And we can easily find the area of a square because we have a square cross-sectional area. And so it's just the length of the side squared, which is 2.3 times 10 to the minus 3 meters squared, which gives us a density of 680,529 amperes per meter squared, which you can write as 6.81. So I just rounded up times 10 to the fifth amperes per meter squared. And in part B, you're asked to find the magnitude of the electric field. So you again use a definition that's given in, first let me give you the equation. So using equation 25.5, you find that the resistivity is defined as the magnitude of the electric field over the charge density. So then the electric field is the resistivity times the charge density. Now you can find the resistivity of copper in table 25.1. So rho is given in 25, and the charge density you just computed in part A. So then the electric field is given by the resistivity 1.72 copper times 10 to the minus 8 ohm meter times the charge density that we just found, amperes per meter squared, which gives an electric field of 0.117 volts per meter. Where I've used this definition that volt is resistance, or ohms, the unit of resistance, times amperes. unit of current. And in part C now, we're asked to find how much time is required for an electron to travel the length of this wire. So we're asked to find the time. Part C, we're asked to find the time. And we can do this by using this equation, that velocity is the distance it needs to travel over the time it needs to travel. So if you rearrange this is just the definition of velocity, and here I put the drift velocity. So we can rearrange the time is the length of the wire divided by the drift velocity. So we already know the length of the wire, and now it remains to find the drift velocity. And you can find the drift velocity by actually using equation 25.3, which tells you that the current density is the concentration of the charges, or the density of the free charges, times the value of the charge times the drift velocity, or rearrange this to find the drift velocity, which is the charge density over the concentration times the magnitude of the charge. And so Q is just the magnitude of the elementary charge, which is 1.6 times 10 to the minus 19 coulombs. So the drift velocity then is 6.81 times 10 to the 5th ampere per meter squared, right? That's the current density that we found. We were given the concentration, 8.5 times 10 to the 28 inverse meter cubed, and the elementary charge, which is given here, 1.6 times 10 to the minus 19 coulombs. So we find for the drift velocity that it's 5 times 10 to the minus 5 meters per second. And then we use a formula for time that we have up here. Time is equal to length over drift velocity, and we're given a length of 4 meters, and we just now found the drift velocity. And this gives us a time of 788. Excuse me. It's 79882.5 seconds. And if you wish, you can convert this to hours, but it should be good enough in seconds.